Ja, ich weiß gar nicht, also müssen wir alle drei.
Ja, ihr seid gut. Also jetzt meine ich erzählt. Zuerst Gesicht zeigen. Genau, eben. Ja, weiß ich. Hallo? Hallo? Hast du ein Mikrofon? Funktioniert das?
Yeah, probably. Hello. Okay. So welcome to the to our short course here on integrated models in population. We called it. It sounds a little bit pretentious here in population ecology and species distribution models. So don't expect much. I mean, it's 3 hours. We can really only kind of touch the surface and yeah. So what we these are my colleagues Schaub, Marc, Kéry, Nicolas Strebel from Swiss Ornithological Institute, and So we're gonna try, and if we have three. We have 3 modules. So the first module, that will be me. I'm gonna try to give an introduction to like the principles of integrated models. And then we have a second module where Nicolas will show an instance of a kind of more complicated integrated model in the setting of an STM, of a species distribution model, right? And then in the end, Miguel will show what he likes best, which are the integrated, but the real IPMs. Yeah, And in the end, depending on whether we have enough time, we may do a little bit of Q&A. So if you have some questions, you say like, you have this study and you were wondering whether you should like view it that way or what kind of analysis, etc. Then we can do that. In between the 3 modules, we plan to do about 15 minutes of break every time, and so that's the kind of the model of the schedule of today in the afternoon. We won't do any exercises, as we said. It's just, too short and would be too complicated. At any time, if you have a question, please either raise your hand, or if say a person who is sitting here on the computer and concentrated here doesn't see it, just speak up. I mean, if they're short questions, we can immediately deal with them. If it's too long, then we might just say, oh well, we have to talk about it afterwards. Okay. Yeah. So here we are. I'm gonna start here. Can you hear me like this, or is this not? Yeah? You still hear it? Yeah. Okay. So I'm kind of sit back a little bit here.
We're hearing, but it's a bit choppy.
So I'm going to talk about try to kind of work out like the general principles in a way of data integration in the context of these integrated models. And so I'm going to speak some introductory slides here about what, why, how, when, and maybe just as important, when not. Yeah. And I will give a very first example of a very simple integrated model in the context of a species distribution model. Yeah, to show kind of the principle of a joint likelihood. And I'm going to focus a lot on maximum likelihood estimation or a maximum likelihood application for this, for my very simple case of an IM, because in the context of maximum likelihood estimation, it's more obviously, it's more easy to see the principle of a joint likelihood as being the product of the likelihoods of each individual data set. But we're going to look at this simple model, both in the likelihood framework and of course also in a Bayesian framework using JAX. Yeah. So what, why, how, when, we're not, and the practical example. Integrated models can be said to be described as a statistical method to share information about some underlying process by combining in a single analysis 2 or more data sets. Yeah? This, as I've claimed in my talk yesterday, I think this is really one of the biggest trends in statistical ecology over the last 30 years. Yeah, and typically the data sets which we combine, they're disparate which means they're kind of different in some kind. So if they would be the same and we would just have like a bigger sample, we would just think of these models as being fitting the same model to a bigger sample size, but no, there is some sort of difference there which must be addressed in the model, which is then our integrated model. And yeah, so we form a joint likelihood with shared parameters among the likelihoods of each data set. And in an interesting paper by Krishna Pacifici and colleagues there in 2017, they talk about, they point out that the joint likelihood is not the only way, the only approach to combining information, but they, in fact, in the context of an STM, they distinguish 3 different methods of sharing information, which they call sharing, correlation, and covariate. So sharing is what we sharing is joint likelihood, yeah, which is what we show. Correlation is something else, which you can read up. It's kind of a less more stochastic, vague relationship between the data sets there with respect to some underlying shared parameter. And covariate is a very simple idea, which is rarely done, which is just take one data set as a covariate in the other. Yeah. So I just wanted to mention this. I like the paper. I think it's an interesting, it's an important paper when we think about integrated models. But the joint likelihood is perhaps the preferred, if you can, because in a way it uses the available information in the different data sets and most directly perhaps exploits most of the information I feel that is contained in these different data sets. Yeah. And so this is what we define here as an integrated model, joint likelihood for 2 or more disparate data sets where there is at least one parameter that must be shared among pairs of data sets. Yeah. So yeah, by the way, I think I have not yet put these slides on the Dropbox. It will be there. Yeah, so sorry. Yeah, so you can get these slides, so you don't have to write up to make notes like crazy. I also gave you a handout on the Dropbox chapter on integrated models from one of our books there, which explains in far more detail kind of what we see as the salient features of these whole integrated models. Yeah. So you can also think of integrated models as really shared process models, because most of the times we have data sets which somehow there is some underlying process which we assume is shared among the different data sets. So this is a picture from this book chapter there on integrated models, where we compare integrated models here in this figure here with just hierarchical models. So in a way you can ignore this bit here up here. But I want to focus on these 3 cases, which I call IM1, well, these 3 different kind of sketches of an integrated model, where the gray you can think of as a model for like a latent process of some kind, and the Greek letters, of course, are parameters, and the red would be like the shared parameter. So very often we have the case, which is this one, and where we have like 2 data sets that directly inform about the same single or more parameters. And to kind of make these data sets, well, to kind of put them on an equal footing with respect to the information about this shared parameter, most of what we do is we describe the different observation process here. So therefore, that's why I have here an omega-1 and an omega-2. So we describe via a different observation process in what respect do these data sets differ in the context of the underlying parameter of interest in the process, which we assume is the same for both data sets. So that's a common one. That will also be the example of my first example of an integrated model that I gave in about half an hour or whatever at the end of this first module. Then the next context would be a model. This would be kind of, the typical integrated population model, where you can see there is a parameter which looks like our usual parameter for survival probability phi. We have a gamma and we have a lambda. So you can think of this as like a sort of the typical matrix model, which is at the heart of most integrated population models. And then some of the data may be directly informative about all of these parameters, like the count data, the count data, typically the count time series, in the typical example of these IPMs, which then Schaub will present in the third modules, whereas other data sets may only be informative about the single one of these parameters in the process model, like, for example, the capture-recapture data, which is only informative about the survival probability here in the entire IPM there. And most of the times we have this data sharing or the shared parameter sits somewhere kind of at the bottom of some sort of hierarchy of process linked processes, but sometimes there may be cases where the shared parameter sits in the observation model. So perhaps if you could think of, like, you do bird survey work, and maybe you have well, I don't know, you do, say, an N-mixture model type of setting, and then maybe you have some other observational data which do not really inform about the underlying abundance, but directly about detection probability. So this is rare, and I'm sure if you really look hard, you will find cases like this, and there is no reason why you shouldn't. A shared parameter shouldn't be in the more observation part of a model, but it's not the common case. The common case is that these shared parameters are somewhere more at the bottom. Yeah. Now, integrated models, or like we say, we like to say kind of the real IPMs here, because there are also other IPMs. There's also integrated pest management, and of course there is also the integral projection model. So could be some confusion. Yeah, so the IPMs, the real IPMs, they have become perhaps the most highlighted example of an integrated model. And so many people use like IPM and IM in a synonymous way. But this is, I think, I prefer to make a difference between IMs and IPMs, because really the IPMs here, they're only kind of a small subclass of a much larger kind of set of models which we can describe as IMs. And to emphasize this point a little bit, here is another thing from the book chapter that we distributed there. This is a very incomplete overview of IMs. It's kind of with kind of the data, the types of data that are combined, and then a key reference here. And just recently, Nicolas pointed out to me that really the good old robust design, so Pollock's robust design is in fact an example of an integrated model, because we combine closed and open capture-recapture data. Yeah, so there's a lot of those, and you see the first. I mean, I have ordered it a little bit chronologically. So some of the first examples is the Burnham model, which combines capture-recapture and data recovery data. So that's 99, yeah, in the 90s. So that's why I said, I mean, it has been, the whole topic of IMs has been a huge thing in the last 30 years. Yeah, and then you see all the other, over the last 10 or 15 years, the whole thing has quite exploded here, and there's really a lot of examples here of those. Yeah. Yeah. Now, in a way, when thinking about how to introduce like these integrated models here, I thought that in a certain way, the principle of an integrated model is not that far away just from the principle of basic parametric statistical inference based on likelihood. Yeah, where we formulate the joint density of the data, of the observed data. So kind of a relationship between what we observe and the underlying parameters, and then we turn it around and use it as likelihood and do parameter estimation. Yeah. So, and in the context of a non-integrated model, where we do this, where we apply this fundamental principle of statistical inference based on a likelihood function, it's completely natural that if we have, like, say, I don't know, like 10 data points, that we normally would use all of them to do the parameter estimation, and we would not, for some reason, like leave two apart. Yeah, and so in the simpler case there, it's just obvious to all of us that we would use all available information, and because more data is better, we typically get more precision. Perhaps we may be able to estimate additional parameters. Yeah. What else? Yeah, and I want to look at this in two maybe just one trivial. Actually, I only go to one trivial example here because I should maybe save some time here. Well, no, I do both. Yeah. Okay. So let's imagine that we have a very simple case of an estimation problem. That we had gone out and counted bird species richness, 5 sites, and what we want to do is like infer the mean and the spatial variation of species richness, so the variability of species richness from within the statistical population of sites from which I sampled my 5 sites. Yeah, and I'm going to ignore here. This is a very, very simple toy example, so I'm going to ignore the discreteness of the data, and also don't forget about imperfect detection and all of these things, and just use for illustration the simple statistical model, perhaps, because everybody loves the normal distribution. So we will assume a normal distribution as a suitable model, kind of statistical sketch of a process that could have generated these data that we have. Yeah. So the data that I'm going to run some Marc code there, but this is kind of a little bit getting a little bit ahead of myself, where I'm going to explain something here. So the data might look like this. Yeah? So imagine that these are counts of the number of species that we had detected at 5 sites. And so if we think that the normal distribution is a suitable model, to make this desired inference about the general average in bird species richness and spatial variability in species richness in the wider area where we did this collected these data here, and this means that we consider each of these numbers here as the draw from a normal distribution, which has 2 parameters, a mean and the standard deviation here. And we have for every single datum here, for every single observation, we assume exactly I just claim in the setting of my little story here, we assume exactly the same parameters. So we have these 2 quantities that we want to estimate. And so to do inference here, we formulate first the joint density, which is like the probability density, which is the product of the densities of each of these random variables, of each single datum. So we form this this product here, and then we kind of turn it around, I like to say, and view it as a function, view this same joint density as a function of the 2 parameters that we don't know, that we want to estimate, and pick those parameters which produce the highest function value as our best guesses, our maximum likelihood estimates. That's the principle of maximum likelihood. Yeah, and so I want to show something here. Okay, I still have a little bit of time. No. So I'm going to simulate some data. No, interesting. Yeah, I think it should work still. Yeah. Okay, then I define the negative log likelihood function, which simply says that I define this R function here, which says that I take the normal density of the data with these parameters Mn, which we call Mn and St, so the mean and the standard deviation, and this means give me the log density instead of density, and then I take the sum, and then I multiply this by -1. So this gives me the negative log likelihood. And this is just a function which I can then apply for my data and throw into a function optimizer, like typically Optim here in R, and find those, and find those parameter values which produce the highest function value of my NLL function. And now what I want to see, very obvious, what I want to show is a very obvious thing, that more data is better. Yeah. So if I only take this first datum here, the first count, which I do here, then I'm kind of screwed because I can't even estimate, Optim throws an error here, yeah, which I don't fully understand, but I mean, well, I understand that I can't estimate two parameters out of a single data point. Yeah. If I take two data points, then at least I get some warnings produced, but at least I get some estimates there already of the mean and the standard deviation. Yeah, which is nice. Then, of course, if I, so we have this function here, which extracts the mean and the standard deviation and the standard error and the 95% Wald intervals here from a fitted model, a fitted model object here, an optimization object here with optimum. Yeah, so these are my estimates here. And then if I have more data points, then my estimates get better. In the sense, so this would be for 3 data points, for 4 data points, 5 data points, for all 5 data points. Now, in which sense better? Look at the standard errors. I mean, the standard errors should really come down. Well, actually, here they go up because there is just one very high number. But just look, in general, they become smaller. And this, of course, what we all know. More data means more precision in the estimates. Then perhaps, okay, so what we can see here is that we already really see some of the features of an integrated model. Although this is not an integrated model, it's just a simple likelihood that we maximize. So, but I like to see some similarities there to this integrated model. So this line or here, I say that sometimes we cannot estimate parameters when we don't have enough data. So in an integrated model, very often it's not. An integrated model, in contrast, is not the amount of data, but kind of different kinds of data, the combination of which may then allow us to estimate the parameter, which we cannot estimate with each individual data set alone. Yeah. And then we get better estimates when we include more data in the analysis. So better, especially in the context or especially in the sense of precision. So usually with more information, we get a higher precision, meaning smaller standard errors, narrower confidence intervals than with less data. So a fundamental principle of an integrated model is always that we have more data, more information. So therefore, we should get better estimates in the sense of estimates that have a higher precision. Yeah, and that's about that, which I want to show here. Yeah. So this is what I said, yeah. More data, more information, less estimation error. Point estimates will typically become closer to the target, and we have more precision. So the standard errors and stuff become smaller. And I think I should do this like this. Yeah. Okay, then this, I think I switch, or no, I skip. So here is a summary then on how and the why of integrated models. So the analogy with just very simple statistical inference based on the likelihood function here, we can say what we just say. I mean, we formulate the likelihood of an integrated model in the exact same way as we formulate the likelihood for just a non-integrated model. We usually on some independence assumptions, we form a product of the densities of each individual data point, and then we maximize this. Or we put it, well, we maximize it with a numerical optimization to get maximum likelihood estimates, or we do the same thing for Bayesian posterior inference with an MCMC algorithm typically. Yeah. And then what we said, similarly as in likelihood, more information is beneficial because we get more, we get better estimates in the sense of having more accuracy often, more precision very typically, and sometimes we can estimate the parameter that we cannot with less information. And the first bit here, what I emphasize here is that just intuitively, I mean, it makes tremendous sense to just explore, to use all the information that you have in an estimation process, in an estimation problem. Yeah. And then the next thing here really is another demonstration now of a real integrated model. For free. So the next thing is I'm going to walk you draft book chapter here, which is on the Dropbox. And so I'm going to work here with an R workspace, which is called Swift, because I simulate data and claim these are data from Swift. Is this, how big is this? Can you see this in the back? Yeah, okay, thanks. Okay, so what I'm going to do here is I'm going to illustrate, well, we're going to look at essentially how we construct the joint likelihood and how the joint likelihood in an integrated model is a product of the individual data likelihoods. So we're going to see this now in full detail. We're going to use function maximization to get the maximum likelihood estimates, and then we implement the same model in JAGs. So again, the point of like the demo here over the next 10 or 15 minutes is to kind of just drive home the idea of a joint likelihood and look at the joint likelihood both in the frequentist framework and also in the Bayesian framework, because both of them have an advantage. The joint likelihood in the frequentist framework is conceptually easier to understand because we can actually see a product of the likelihoods of the, we're going to see the joint likelihood as being defined as the actual product of the individual data likelihoods. But this is not the favorite, this is not the best way in which you implement an integrated model unless you're a statistician, because for most of us as biologists or so, specifying the same integrated likelihood, the same product of the individual data likelihoods in the kind of more intuitive way in the box language, in software like JAX or Nimble, and a little bit less so, but also a little bit in Stan, this is by far the preferred way how to specify these integrated likelihoods and therefore how to fit these integrated models. And this is, in my view, this is the biggest kind of the doability or the kind of, yeah, that us biologists, we can fit these complicated integrated models with software which happens to implement the Bayesian mode of doing statistics, so originally Winbox and then JAX and Nimble. This is the main reason why really in the field of integrated modeling, integrated population modeling, Bayes has become completely dominant, because it's just so much easier to specify, to fit these models in Bayes as opposed to maximum likelihood. But we fit the same models, it's just Bayesian inference for the same model. We should usually, and then we're going to see this here also, when we do Bayesian inference in the way that most people do it, namely with so-called vague priors, where we try to minimize the amount of information that comes into the estimation task from the so-called priors. So when we use vague priors, then we will get numerically numbers, estimates that numerically look practically identical to what we get from non-Bayesian, so from maximum likelihood estimates. Yeah. And again, conceptually, I really like it, and it's useful if you see a simple integrated model, the maximum likelihood way, because there we can see the product, which we cannot see in JAX. Okay, so the setting is that I claim, yeah. So I claim, or we're going to simulate 3 data sets, which we claim are from Swifts, and we have counts from just some counts at the number of sites, and we have 3 different like versions of counts. So first we have regular counts, yeah, and then we have 2 versions of counts which have some sort of like a degrading of the information, of the original information. So first we assume that we have some lazy bird watchers who never record the zeros. This is pretty common. This is called, well, it's kind of the count variant of presence only data, if you like, yeah. So, and then the third thing is that, okay, and these data, then they're called zero truncated. So we never observe the zeros there, yeah. But we can do statistical information, we can do statistical estimation also with such distributions where some observations in principle are never observed. They're called truncated, or in this case, zero truncated distributions. And then in the third data set, we're going to work, or we're going to invent, and then see how we can work with another kind of form of count data, where we just distinguish a count of 0 and counts of greater than 0. These data are called also presence absence or detection non-detection data. Yeah, and so we're gonna think about. Oh yeah, good point. I love these points. Sorry. Yeah. So, but it's much better for. Thanks, Gonzalo. Okay. So these are the three types of data, and then we're gonna see how we can fit how we can formulate and fit an integrated model. These are some beautiful Swifts, which I copied from the internet, of course. Yeah. So we make a couple of comments here. Yeah. So here, this whole line. Can you still see this when I highlight this, or is it? Yes, you can. Okay. So here I make a brief comment that usually we have a very strong, me and a couple of colleagues, many colleagues, we have a big preference for like species distribution models, which have an explicit representation of the false negative detection errors, detection probability or so. But here, for just illustrative purposes here, we forget about imperfect detection because we want to illustrate the concept of an integrated models in the simplest possible setting. So we ignore imperfect detection. But this is not meant to say that, oh, Kéry has been fitting an SDN there with integrated, whatever. Yeah, don't forget this. And the other assumption is, and this is kind of a big thing here. Well, we assume that the three data sets are independent. And independence, I mean, independence in the context of these integrated models, I think is an somewhat elusive concept. And as you have seen in the talk, for example, by Frédéric Bacon, there is some debate or some uncertainty about what independence means or different kinds of independence or so. Yeah, so take this here with a grain of salt. But just for the construction, for the way how we're going to construct the integrated not the integrated likelihood, the joint likelihood afterwards, that requires that the three different data sets that we combine, that they're statistically independent, because only then is the joint likelihood of all the data equal to the product of the likelihoods of the individual data sets there. Yeah. So here I'm going to say that I assume independence because I claim that none of these counts are taken at the same site. Yeah. If the counts are, I do believe, in spite of Frédéric's talk, that in this case here of this type of data, that if you have no overlap of sites, that this will mean that the data sets are independent. But I'm not completely sure about this. This independent thing, again, in the context of integrated models, I think is something that should be investigated more so that we can better understand it. Okay. So then we have these data, afterwards we're going to simulate them, but here just in my story, imagine that we have these three types of data. So what we want to have a statistical model to learn something about the parameters. So what would be used for statistical models? They're pretty simple. I mean, the first ones are just these counts, and I assume that these counts are made, that all of these three data sets are collected along an elevational gradient. So I'm going to, in my story, I'm going to say I want to estimate like an elevation gradient of abundance. Yeah. So we have these counts here for the first two data sets. The second data set there has no zeros, so that's a complication. So for the first data set, just having these counts, non-negative discrete numbers. So the typical statistical model, of course, is a Poisson distribution. So we might invoke a model like this here, where we say that the count at site I for the superscript here means the data set. So it's the first data set. These are Poisson random variables with an expectation with a mean here, which I denote by lambda, which is also indexed by I. So it's allowed to be different for every site. And then to do linear modeling with a covariate here, I do this on the scale, the scale of a transformation of the mean. So I have the link function, the log of the expected count here, and express this as a linear function of this covariate elevation, which is also indexed by I. So of course, every site has a different elevation there. Yeah. And then for the data set 2, a naive analysis for the data set 2 would, of course, the data set 2, which has no zeros, yeah, which is zero truncated. Because very often when we go out and we don't see a thing, we tend to forget that the 0 is a datum just as well as a 1 or a 10 or a 15, yeah? So we tend to confuse, I like to say, we tend to confuse missing values and zeros, yeah? So when we have a 0, then this is more likely to end up as a missing value, say in the databases like Ornito or Biolovision or eBird or whatever where we put our data to. So here I say in the second data set we do have all these fundamental missing values, so we do have to account for them, and it would be wrong to fit the same model here just to the zero truncated version of the box. And then for the third data set here, for the binary detection, non-detection data, in principle, we might write something like this. So this is 0-1 data. So the typical model for that is like the coin flip model, a Bernoulli distribution with a success probability, which here I denote by this fork type of Greek letter, which is a psi, yeah. And then, yeah, this would just be a logistic regression. So the logit transformation of this expectation here, I would again express as a linear function of covariance with here different parameters here, because they're superscripted by 3 for the data set 3. Yeah. Now, now I have a problem, and this is a typical case in integrated models that we have. I have really these different data sets, and intuitively all of them contain some information about something underlying in which I'm interested in. Spatial variation here in abundance, in density. But they're like in different currencies or so. So here I have occupancy, and in the other thing I have an expected abundance. So how can I bring them together? And yeah, and so the key to data integration, to integrated model, is always that you must somehow describe all the data sets using some common currency, by which I mean, in a way, a parameter. You must somehow describe all of the data sets as a function of at least one parameter which occurs in all of them. Yeah, this is the principle there of data sharing. And so here we have we have this abundance, we have this density parameter here. We're going to see, or I'm going to relatively quickly show how we can get the density parameter also for the case of a zero truncated distribution, a zero truncated Poisson distribution. But here we have this, this occupancy parameter, and a priori it's perhaps not so clear how we should link an occupancy there with an underlying abundance. But there is a magical, one of the couple of magical tricks in statistics is a thing called the C-log-log link, complementary log-log link, which has, it's a very esoteric, it sounds very esoteric, and normally we never use it, but it should be our favorite link, link function for binary regression models, because it means, and I'm going to skip over the whole explanation here really, but what it means is that if we apply the C-log-log link, if we apply the C-log-log link to a probability which represents like occupancy or something, then we model the binary data as a function of an underlying abundance process. Yeah. So by simply applying a complementary log-log link, fitting our binary regression model there, our Bernoulli regression model with a C-log-log link, the parameters that we estimate, they have the interpretation, they refer to an underlying density there. Yeah? I have to think about this. It's a fantastic link, and this is one of the ways in which we can link presence absence data with counts. Yeah, with detection non-detection binary data on occurrence of species with counts. Yeah, and what else? Yeah, so this is what we're going to do here. Okay, we do some data simulation here. What we're going to do here now you see me at executing R at my best. I copy paste from a Word file. Yeah. If it's too fast, so I hope it's not too fast going back and forth or so. But I try to give ample explanation what I'm doing here. So what I'm doing, I assume that I have different numbers of sites because typically typically in integrated models we have we have kind of a how should we say, like a trade-off between the amount of data and like the information content of the data. Typically we can distinguish some types of data which are copious, which we have a lot of, but which contain less information, or at least where it's harder to extract the information from them. And then we have other data which are more information rich, or where it's perhaps easier, it's more directly obvious how to extract the information about certain parameters. So in this case here, it's obvious. I mean, the counts are in a way that the counts are what I would call the most information rich data. The zero truncated counts are already a little bit less information because we have lost some information about the frequency of the zeros. And then the detection, non-detection data, they are quite a bit less information rich. Yeah. But because usually collecting more information rich data is logistically harder. So it's a very typical case that we have the largest sample sizes for the most information poor data, and we have the smallest sample sizes for the most information rich. So just to kind of emulate this law of nature of citizen science and other types of data, you might say, I say that I have 500 sites with counts, 1,000 with zero truncated counts, and 2,000 with detection non-detection data. And I'm going to simulate this data by starting with counts, with regular counts for all of these data sets, and then I'm going to degrade, so as to say, the data set 2 and 3. Yeah. So first I'm going to simulate these the data sets, and this is up to here. Regular counts for 3 sets of counts, which have C1, which is 1 set of counts. Yeah. And then I take the second set of counts and I throw out all the zeros. This gives me my zero truncated data set number 2. Here I make a copy of C2 and write it into ZT, Z2, and then here with this line here that I'm highlighting here, I only retain those elements of the vector ZT, Z2 which are greater than 0. So I toss out the zeros, and the result then is of course also that I no longer have 1,000 of these. Oh yes. Oh yeah, no, the zero truncated. So no longer have 1,000 values of these counts, because I've lost the zeros. I'm only left there with a data set of 720. Not important for the analysis, but maybe good for you to understand how the things work. And then for the third data set here, I just squash them into binary. So here I say that every count which is greater than 1 will be overwritten with the 1. So here, for the original regular data, which look like this, when I quantize them, when I squash them to binary data, then I keep the 528 zeros, but all of the other ones get reduced to just 1, meaning a detection, meaning a presence. And okay, and as always, I run out of time here. I should make some shortcuts. Importantly, this is just a visualization of the data. So here we have the data sets 1 and 2. I think the black one is the data set 1. So these would be 1,000 regular counts. The gray one should not have any zeros. I hope so. And these are the zero truncated counts produced by the lazy bird watcher. And then we have 2,000 data, a sample of length 2,000 here of just binary detection, non-detection, or presence absence data. So these are my 3 data types, very common data types in the context of species distribution modeling. Yeah. Kind of one kind of level below that in terms of information content or so, or hardness of estimate, or hardness of more or difficulty of modeling would be presence only. So presence only would get it if you take these data here and you throw out the zeros. Yeah, that gives you presence only. Okay. I'm not gonna, yeah, it's always takes longer than than what I wanted. I have to speed up a little bit, and you can read it up at ease tonight. So I'm gonna, when we do integrated models, when we can, we almost always will fit the simple models. We will take one data set. Well, we fit each individual model to each individual data set first for several reasons. And so this is exactly what I do. Well, for several reasons. Why? Because it helps us to like write the code, understand the model, and then also it's often when we do complicated things with models, for example, or with complicated software like JAX and these types of things, it's easy to make mistakes. And so when we do kind of a progression of models, then it's an interesting thing to well, how should I say? If you suddenly get very different estimates from one model than say from a neighboring model or from a slightly simpler model, then that may raise a flag. So that may mean that something went wrong. Not necessarily. It could be that a more complex model, for example, that this just really you get kind of suddenly get like a negative relationship somewhere where before, where before you had a positive. It's possible, but still, yeah. So in a similar sense here, also in general, I mean, to me, the most important modeling principle is start simple and then incrementally make your thing more complex. And so applying to integrated models, this is what we do here. We start simple, we fit the individual data models first, and then only then do we put them together. Yeah. So what I'm going to do here, maybe, yeah, so we start first with the first data set, and where we do maximum likelihood estimation. And because I'm wrong here already, I'm just going to have to speed this thing up here. And I have to think about how. Anyway, in the first data set, when we just fit the good old Poisson GLM, yeah, then these are but doing it the kind of doing it on our own way here with specifying a likelihood function here or a negative log likelihood function, and then combining that with the data and using the optim function there to do function minimization here. And these are the estimates what we get here. Yeah. Then if we do the same thing in JAX, then well, you know, this is how a Poisson generalized linear model looks like in JAX with a single query. So I'm going to run this. Most of the purposes. Here we're done. Mixing, so have the chains converge. Yes, they have. They look wonderful optically, and the star hat thing also is close to 1. So that looks good. And then one thing I want to emphasize, and one thing I always emphasize in courses and stuff, is like, again, how here, I mean, we don't have the time to go into the JAX model here, and this is not, of course, about Bayesian inference, but just to say it once again, that if we do what we mostly do, namely use so-called opaque priors which try to minimize the amount of information that goes into the estimation, then numerically we end up with estimates, both of the point estimates and also the uncertainty, that are essentially indistinguishable between maximum likelihood and Bayes, unless you have very small sample sizes or unless you're in a very strange situation, which may sometimes happen. So what we see here is we have the intercept and the slope, we have the maximum likelihood estimate, the asymptotic standard error, and these are the corresponding the point estimate and the posterior standard deviation from the Bayesian inference. And if I look at this, then I claim they're identical. Yeah. And this is what we always get. So for the second data set, we have to fit the zero truncated GLM, and this is what is explained here. And there is apparently a function in R which can do this called VGAM, so I have to check this. But in the meantime, here is the negative log likelihood function for a zero truncated Poisson. Yeah. And we can optimize this just as well as before. But because I ran these models already in my R workspace, which was named Swift models, I don't have to do it. So I'm just gonna go down here. I have a quick digression here about what happens if I just fit the wrong Poisson model. If I ignore the zero truncation and just fit an ordinary regular Poisson regression model there, I will overestimate abundance quite a bit, depending on, well, how frequent the zeros were. But yeah, so that would be wrong. Zero truncation has to be accounted for. Now in JAX and in Nimble as well, and no doubt also in Stan, you don't have to worry about the likelihood of the zero truncated distribution, but in fact there is this argument here which you can use just T, and then you can specify a truncated distribution here like this. So that's very easy to fit such a zero truncated Poisson distribution in this case, which I do here. And if we compare the estimates in the end between our do-it-yourself maximum likelihood estimates here and the base and posterior inference, we see again the same thing, numerically identical estimates. So we can probably trust the base, if you like maximum likelihood, better because it gives you numerically the same numbers. And then for the famous C log Bernoulli GLM here, we can, by the way, also fit these models, of course, with just the function GLM here in R by specifying here the link C log inside of the argument here of the family of the distribution here. But we can also specify it ourselves in the likelihood function here. And this is what, well, this is one way how we can specify the C log link actually. Yeah. You get all that, or I don't have to take a photograph. Yeah. And in JAX, yeah, in JAX, I think we do have the C log. Yeah, we do have a C log. So I just say C log of the probability there, and then I specify the linear model there in terms of the covariates. Yeah. And then the final thing. So I have about 7 minutes left here. So now we want to do this, the grande finale here with the integrated model. So we're going to first fit the integrated model with our do-it-yourself likelihood approach here, where, just to remind you, and what you've read a lot of times, what I've emphasized now a lot of times, that under the important assumption of independence, that these three data, or the data sets that you combine in an integrated model, are independent statistically, not necessarily biologically, but as Frédéric Balcon emphasized, it's the statistical independence that's really at the heart of or that's required for constructing the likelihood in that simple way as a simple product. So if we have this, then we can simply multiply the likelihoods for each individual data set, and that's our joint likelihood, and we can maximize that using our function optimizer. Yeah. Or because for numerical reasons we never work with the likelihood, but we work with the log likelihood, or actually the negative log likelihood or so. So what we do here is we define this negative log likelihood function, the joint function here, as the minus of the sum of the log likelihoods there. Yeah. So to specify, to do our own do-it-yourself maximum likelihood as inference here, we define an R function as usual. So here I simply like added different arguments here for the response and the covariates. So for the counts, the zero truncated counts, and here the Y3 would be the detection, non-detection with their associated values of the elevation here. Yeah. Then we have the parameters that we want the function to maximize there, and then we just specify these different. I first specify the individual data likelihoods here, which are called L1, L2, and L3. And here now, down here, you see the joint likelihood. And remember, a sum of logs is a product of the actual thing. So here you see the sum. That's a joint likelihood here. Yeah. And because optim is a function minimizer and not a function maximizer, well, okay, we take the sum. And then because optim does minimization and maximization, we just put a minus sign in front of it. And then we can use this with optim there. And yeah. this. I think I just want to execute. Look at this. That's our integrated model here with our own likelihood inference. I think I was really proud when I did this. Okay. And then what about JAX? Now in JAX, and this will be the way how most of us will always fit their integrated models. The principle of like this multiplication of the likelihood in a way corresponds to just stacking models for the different pieces, for the different data types, one underneath the other or one on top of the other inside of the same model statement in the box language. That's all there is. And of course, in these different parts of the whole model statement that describe one data set, the next data set, and the third data set, some of the parameters must bear the same name. Yeah, if you put different names, then you will just fit like three separate models to the same to these data sets separately, and there will be no data sharing. So the key thing is stacking these models in a single model statement and having some parameters for different data sets have the same name. And this is wonderfully easy, but it really hides the kind of conceptually, statistically what goes on, which is that we're working with a joint likelihood, which is a product here. Yeah, but we're doing the same thing, just in a way which is far more attractive to us biologists. Yeah. So in JAX, we have there's 100 ways how we could format the data input here. Here I just give these 6 vectors of the counts and of the grades here, which is elevation, and then the sample size. These are those. And then the data, not data, model. So here we have this model statement, model, and then an open parenthesis. We have the priors, and here I just have joint likelihood is just created by specifying a likelihood for the first data set, specifying a likelihood for the second data set, specifying a likelihood for the third data set. And we have shared parameters. We have parameters that have the same name that occur in 2 or more of, well, in this case, in all 3 of these likelihoods for the individual data sets, because the alpha and the beta here, they have the same name. So this means they will be estimated as a single parameter. If I instead, like this, for example, 3, and then I would also have to change in the prior something. But if you look just at the likelihood, the joint likelihood here, this would no longer should no longer be called a joint likelihood. By fitting this model here, in essence, you would get exactly the same estimates as if you fitted each individual data set alone. Yeah, you just do it as all at once, which is nice. Yeah, or in contrast, if you did, for example, this, then you will only share you would only share the information here for data set for zero truncated Poisson, the detection, non-detection. Yeah. But in the original, by having all 3 share the same name here, we share the information across all 3 data sets. Yeah. Oh well, I shouldn't save it. No. Okay, and if we execute this model, I ran it, I have it run already in my R workspace here. I get some estimates here of these parameters, of the intercept and the slope on the log scale, and then because I like to think of birds not on the log scale but on the bird scale, I translated this also on the natural scale. Then the important we want to make the comparison again between maximum likelihood estimates and the Bayesian estimates, and these are here on the log, parameters on the log scale here. So once again, for practical purposes, I claim these are identical. Yeah. And then the final thing I'm going to present here in this little practical here is that we want to see, so the basic benefit of doing such an integrated model is always you have more information, so your precision should increase. Yeah, so we want now compare our point estimates and the precision across the 4 different analyses that we ran. We have one analysis for data set 1 alone, data set 2 alone, data set 3 alone, And then we have the integrated model for all three data sets at once. Yeah. So here is a tabular representation of the point estimates and the standard errors, but it's hard to see the patterns, so therefore we make a picture. And the picture where we plot the point estimates and not the standard errors, probably convert the standard errors to the so-called bold 95% intervals, and here we confidence intervals. Here we have them. And so what we see here, we see for the intercept and for the slope. Model 1, which is just the regular counts. Model 2 is for the zero truncated counts. Model 3 is for the detection, non-detection data using the magical C-log log link. And model 4 is our integrated model. And the same here for the slope for abundance. Yeah. So what we see here is you should perhaps a little bit ignore, don't focus too much on where the dots are, the point estimates. So the point estimates should in fact be unbiased. So this is probably just randomness of sampling randomness, that for example, this is lower down than this, yeah. But focus on the uncertainty of the estimate. So what we see here is that the uncertainty maybe, yeah, here, probably the uncertainty gets a little bit bigger when you go from here to here and to here. Because the original data, even though we had increasing sample sizes, but still the from going from the counts to the zero truncated counts to the detection, non-detection data, the information content declines because we lose information by kicking out the zeros or quantizing everything to 0, 1. Yeah. And what's most remarkable, or what's kind of most pertinent for the subject of this workshop here is that the integrated model has by far the best precision here, because the 95% confidence interval is far smaller, far narrower than for the individual data sets. Yeah. So here you see that. And the same thing here also with the covariate effect here with the slope, where we also see that we have the best precision here from the integrated. That's really it. I think I have a final slide. Yeah. So, yeah, so overall, yeah, we claim, and many people think, and I think that integrated modeling is good, because if you have multiple pieces of information on the same inference problem, meaning say that somehow have to do with the same parameter, then it probably always makes sense to at least consider exploiting all of this information, yeah, in a formal way. And this formal exploitation of different types of models, different types of information, this is an integrated model, yeah, where you get all of the associated advantages, which is more precision. And sometimes what I haven't shown here really, but I think which maybe Nicolas will show, or what is famous in the integrated population models, that by combining different types of data sets, quite often we can suddenly estimate certain parameters which are not estimable from the individual data sets alone. Yeah. So, but there are costs also of using an integrated model. So the models are really more complex. They're harder to understand. They're harder to build. They're harder to fit, and they're harder to explain to others. Yeah. So there's a whole complexity cost there of these integrated models. And so therefore these costs of this added complexity that must be more than compensated for by the benefits that you gain of an integrated model, which is increased precision and or the ability to estimate additional parameters. Yeah. Also, what we shouldn't forget in our kind of excitement about being able to like use all the data sets, that some data sets perhaps are just rubbish. Not every data set that you find kind of lying under your doormat is worthwhile being used, is worth your time for doing an analysis with it. Yeah. So we should really think about, yeah, which are good data, or yeah, because by adding a data set in a model, you always incur costs to make a model more complex. Yeah. And perhaps very often, if you add different data sets in an integrated model to kind of describe how this different data set relates to the rest of the data or to the parameters that describe the rest of the data, often you have to employ new parameters. For example, new detection parameters for the new data set over there. So there is an inferential cost of having an additional data set. And we should be critical and try to like gauge the value in a way of each individual data set and then think, should we really put it together? Even though it's fun to make it, it's sexy because everybody wants to do integrated models, population models or so. It's not the case that we should always do this. And the decision should also, the decision should also, whether we should integrate or not, should also depend on the objective of the modeling. And what's the objective, the goal of a model? That's one of the most forgotten topics in modeling, I feel. We should always be clear about what exactly do we want with our model. So, for example, my favorite example here in the context of whether or not we should integrate in the context of integrated population models is when in a typically integrated population models, as you will see in the third module, we combine counts with capture-recapture data and possibly also have fecundity data. Now, if we have these three data types, but all we really want to do is estimate the population trend, then possibly we don't need to do a complicated integrated population model, but we can just fit some Poisson regression to the counts. That may be better and easier and much more direct. In contrast, if you're interested in survival estimates or so, then perhaps it may be best to just take the capture mark recapture data, do a good old Cormack-Jolly-Sieber model, and do not go the full way to do an integrated population model. Yeah, like this. And yeah, then the final thing here, probably I forgot once or two, so it's always good to look a little bit into the future. So what are things that are, and Miguel, perhaps if I have something important here forgotten, then please correct me or add to it or so. So what are important like future research avenues for integrated models? So one thing which is really fascinating and where we should learn more is about where does the information come from and go. Yeah. So for example, it would be nice if we, or in an ideal world, for example, we could say we could somehow compute some metric and say something like for the estimate for survival rates, like 98% of the information comes from the capture-recapture data, 1% comes from the counts, and 0.5% up to rounding error comes from, I don't know, the fecundity. So something like this would be really interesting and would also help us, for example, in our decision whether we should combine or not. Yeah. Where does flow of information? I mean, in our book we have a bit on that and how you some ways how you can study this or so. But I think there's a lot more to be learned, to be investigated about this. Well, actually, I mean, this is really the same thing here. Contributions of different data set to estimate parameter in the model. Yeah, goodness of it, the good old goodness of it. I mean, there's some things. I think BSBs and Morgan, they have some things, some sort of parametric bootstrap type of thing in for likelihood inference with Bayes. You can do some posterior predictive checks or so, but goodness of it in general is a under research topic in all of these complex models that we do, but it's also a very challenging thing. Yeah. And then this whole thing of independence, I mean, it's yeah, this is an important thing also, I think, where we should understand more. Yeah. Other than that, I mean, there's just a million different ways how you can try to combine 2 million different kinds of data. So that will be one of the main research or one of the main ways where human ingenuity will lead to progress in integrated models. Is just by like thinking about how we can combine different types of data. But in general, do you think there are any other big things or so that you? Yeah. Okay. Yeah. Well, so that's about it as an attempt of kind of giving a kind of setting the scene a little bit about integrated models. We would make. Do you have any specific question right now, or Gonzalo? Just shout, or maybe you can stand up, or I don't know.
If you were to make, in your example, 3 different combinations of two rates, what's the effect of the moving one?
Yeah. That would be one way. That would be as well. That would be one way of like gauging or assessing the amount of information. Yes. Yeah. Very good. Yeah. Kind of additional subtraction in a way or so. Yeah. Or going the other way, like taking one and then adding in the other and see how by how much you reduce your standard errors or things like this. Yeah. Yeah. Thanks. Other question? Okay, so let's make a break. It's 42. Let's make 15 minutes. Yeah? Yeah, we meet again at 3. 15 minutes of break. We gave you, the Swiss gave you 5 more minutes than the French. Yeah? No, that's German, Gonzalo. Hey Miguel, was? Ah nein, jetzt bist ja du, Nicolas. Was muss ich jetzt machen? Jetzt musst du den bei dir reinstecken, oder wie?
Ja, was ist das?
Ja. Matt?
Am Schluss.
Ja, ist gut. I can just, Matt, we can just pull it out and then, yeah, okay. Yeah.
And we've got, you've given us 15 minutes to fix it as well, which is perfect.
Super cool.
Thank you, I'm glad. Yeah.
This is perfect, like an introduction and to understand all the stuff was really clear. And,
Okay, thank you very much.
It's also really empowering to think about integrated models more generally. To think about the integrated model more generally. So definitely be thinking about integrated models using different network data sets.
Yeah, well, of course, I mean, that's really cool stuff. I mean, I don't know anything about this network models, but I mean, I think that's a big part of the game. You have new type of data, and then you have an interest in combining it. Well.
it's like a philosophy, actually. Huh? It's like a philosophy, like to find the things that put together the different sources of data and look for what they put together rather than the things that separate them.
Yeah.
It's a
Yes,
kind of,
yeah, also.
Should have asked him the question when you invited it, but wanted to make it missing. So you said about assessing like the relative amounts of data, right? Like 90% the information from the CMR.
I was just dreaming. That doesn't exist.
Yeah, okay.
That doesn't exist. I want to say, or I think I said something like in an ideal world, we would have some way of coming up with such a metric, or such an assessment. But there's qualitative ways in which we can get the feel for how, in a way, how sensitive like estimates are to the amount of information. For example, well, you could think about it like Gonzalo there suggested, like taking away a data set or so, or you could like, rather than taking away a full data set, you could also go like incrementally, like taking away a quarter of the data set, half of the data set, 3/4 of that data set, and then see how sensitive like the standard error or the posterior standard deviation, how sensitive the precision is, how much the precision reacts to these increases or decreases of the information. Huh?
Yeah, of individual data sets.
Yeah, but of course, yeah.
Yeah, I hope. Probably before the people that listen via remote didn't hear, because it looks as the microphone was mute.
So,
Mark.
no, I muted it when we started the break.
Oh,
I
okay.
can have the power to switch it on and off. So when you started chatting to people, I thought I'd just.
Okay, yeah. Someone
So no, it was all good. I was
participants.
keeping an eye, and no
Okay.
one complained on the Zoom chat. I kind of figured if something was wrong, someone would say on the Zoom chat. So. You want me to go and try and get people to come back in?
I think they need the bell. They are that much used to. Yeah. Can we start, Matthew? Was habe ich? Du Wasser da, ja. Ich bin bestens ausgerüstet. Matthew, are the participants muted? Yes. Or yes. Okay.
You should be okay, I think.
Yeah, I'm.
Yeah.
I am.
I'll ask a question using chat in case it's over.
Okay. Hi all. So welcome to the next part of our workshop. Just quickly, I'm not sure if those that are sitting behind will really can read that. So you still have the possibility to come closer if you feel like. Don't need to. Right. And I think we didn't have the bell and you're so conditioned, so we are a bit late, sorry. 3 minutes. Have to mention that as a Swiss. All right, I will talk about two things. One is integrating count and detection, non-detection data, but in a hierarchical model, in a binomial and mixture model. This can be particularly useful is, for example, count data is sparse, count data is often more expensive, and detection, non-detection data more abundant and less costless. Often also has a better spatial coverage and so on, or a wider spatial coverage. Yeah, Marc mentioned that there are many different methods. For example, you can fit a separate model with your detection, non-detection data, and then use the outcome as a covariate for an abundance-based model. What I will show here is a joint likelihood approach. I think it is most explicit to really combine the different data types into one model. And I will do it in JAX. Yeah, and then in the same script, I will check whether including detection, non-detection data really improves the resulting predictions or the prediction ability of the model. You can find the code on Dropbox. There is also one useful reference on the code on the Dropbox, and yeah, I'll basically run code. Try to talk about what I'm doing with the code. Can you see it more or less, or those that want to see it? Yeah, fantastic. And yeah, please always ask questions or let me know when I'm too fast or when I'm whatever, when something is not clear. Yeah. So first I load the library raster just for plotting, and the analysis will be run with JAX UI. I load the data. Data is similar to what Marc has shown before. We have several sites. Data comes from different days of the year, Julian date. Two different data sources. One is count data and the other is detection, non-detection data. Spatially, we have some overlaps. So some sites with count data also were visited by people that just made checklists. So yeah, detection, non-detection data always comes from checklists. I'm not inventing non-detections, but really deducing non-detections from checklists. And rep, that means some sites were visited multiple times at the same Julian date. This is because there can be several observers going to the same site, but also because I pooled data over more than one season. These are the detections. It's either 1 or 0 typically, but if there are more than 1 reps, then could be also higher than 1, of course. And then I also have number of individuals, but in the data set, that's the counts. But in the data frame, I either have for counts or for detections, I have NA. That means it's either count data or detection non-detection data, but it's very useful to have it in the same data frame for the analysis afterwards in checks. And it's about the bird species common white throat. Then I have some covariate data on buildings, elevation, permanent forest cover, grassland structures, hedgerows and stuff. It's also important for that species. And the spatial grid is basically, or spatial unit is basically 1 km² grid. Then I do want to make predictions for the for a whole grid, not just for the locations where I have data from. And so I somehow have to link, but I have covariate data for an entire grid, for an entire landscape. So I have to combine the observation data with these covariate data. That's what this line is for. Then I quickly visualize the data. This is one covariate, elevation. Yeah. That's just a tiny part of Switzerland. Yeah, I cropped data. Also the data, yeah. I reduced the data for convenience reasons for the workshop, of course.
So you can run things in the workshop.
Yeah. Yeah, thank you. We have count data from 39 sites only, not a lot. These are the count data. Black means count of 0. Blue means what's the highest was 5, and yeah, red means 1, and that one is something in between, maybe 2 or 3 or something. Yeah. Yeah, then we also have repeated visits in the count data. That's quite useful to estimate detectability. So yeah, some sites were repeated visited by counters, and some sites were repeated visited by people that filled checklists. Then these are the casual observations. The black are the checklist observations. Black means species was not observed, and red means species was observed, and the darker the more. I think I have also plotted that a bit bigger. Yeah, and then it looks like that. So as you can see, for that site, for example, we have the species was counted, and it was also observed in checklist data. You see my mouse? Yeah. Okay, and the background is elevation. Could also be another covariate. Yeah, and as mentioned, I really reduced the data set a lot. So it probably doesn't really fit the purpose, but if you really want to do or want to do an analysis, probably too small. Proper analysis, probably too small. And yeah, then I skip count data from 10 sites. And then we will afterwards predict the count data for these 10 sites based on the model estimates. Actually, yeah, skipping data from 10 sites only is way too few, as the results of the comparison yeah, might be strongly might depend on whether the skipped sites really, yeah, are outliers or not, for example. So typically you skip 10% or something. These are the coordinates of the 10 sites. And that's then the data I have left out. It's now just count data, and I do not, I keep all the checklist data. Yeah, here I remove it from my data, and I can just quickly show the visualization of it. So these are the 10 sites that I have crossed out, yeah, and from these sites I just removed the count data. So the detection, non-detection data, they are still there. Then I go to the checks analysis. First I prepare the data. What do we have here? The number of sites with data. Oh, no, all with and without. Y are the detection, non-detection data. A small n are the counts. Number of visits per site, as mentioned. Sometimes they were visited repeatedly, same day. And then whether it's count data or checklist data, this vector linking the covariate data with the observation data. Same for those that I have skipped. Number of observation data and number of observation data that I have skipped. And I add the covariate data. Covariate data is scaled. So that's the data that then afterwards will enter checks. Parameters that we want to look at when analyzing the data. Then I have to prepare some initial values so that checks doesn't crash when starting to run. For how long do I want to run my chains? These are the setting here. The number of iterations, number of burning, thinning rate, and number of chains. Hope you're more or less familiar with that. Yeah, as you can also interrupt me and talk more about that. And then here comes the model file, and I have two different model files. One is just the binomial mixture model, and with the binomial mixture model, I will only analyze the count data, so the count data that are left over. And then I have a second model that analyzes both together, the count data and the detection data. So first submodel is about the latent state, about nature. We go over all sites, and well, for each site we estimate a latent abundance, as a Poisson outcome from lambda, and lambda is product of, or is, yeah, depends on an intercept and the effect of the different covariates. That's what I specify here, linear predictor. Yeah, that's basically a GLM. Then the observation model, that's the observer, not nature. Or it's kind of a thinning process because the observer does not see everything that's there in nature. So N, as mentioned, that's the counts that the observer bring home. They're binomially distributed. P-int, that's the detection probability per individual, let's say, territory owner in a site. And N comes from here. That's the latent true abundance at the site. So small n will typically be smaller than large N, as long as detection probability is not perfect. Yeah. And then with that part of code, we predict the out of sample observation data. So we go over all data that we have excluded. And for these, we kind of predict small n. It's yeah, kind of equivalent based on the estimated detection probability and the estimated true abundance from here. So yeah, this line and this line, they are basically equivalent, but that one here, that doesn't enter the model as data. And
Could you repeat the line 95?
Yeah. So here we or NOOS, that's the count data from the site that we have skipped, from the sites that we have skipped. And yeah, they are also binomial outcome of detection probability and latent abundance. And then we have to indicate some priors. Save that. Yeah, that was the binomial mixture model for count data. And now there comes a binomial mixture model that allows us to combine count data and detection on detection. And here again, we have latent abundance, Poisson outcome from lambda, and lambda again, as before, for that we estimate an intercept and the effect of the covariates. Then we go through all observation data. And here the counts and the detection non-detections are included. Again, these are the real counts. They depend on detection probability and latent abundance. And here we estimate different detection probability for either count data or detection on detection data. We could also assume same detection probability, but typically during the counts, people spend a bit more time in on a site, and therefore, yeah, it makes sense to estimate that different separately. Then the other data type, that's the detection non-detection data, is in this case here is also a binomial outcome of detection probability of all individuals together in, or all territory owners together in that site. And here the number of repeats, the number of visits at that day and that site. But typically in an occupancy model, this is just a Bernoulli because you don't have multiple visits. So it could also be a Bernoulli of detection probability. And that line here, that is the Royal-Nichols formula, means that a detection probability of all individuals together is 1 minus the power of 1 minus detection probability per individual, to the power of the number of individuals there. Maybe I can plot that or try to visualize that. So here we say that one individual has detection probability of 0.2. And so if there are more than one, then detection probability kind of increases and approaches 1 if n is infinite. And then here again, we predict the count data for that part of the counts that was skipped, similar to what as we did it in the N-mix model. Again, priors. Now we give priors for both different type of detection probability for 2 different sources. Save that, and yeah, then I can run the model in JAX. Like that, it doesn't take that long. I load the data from a longer run. And yeah, this is now just the N-mix model based on the counts. So we can have a look at the results. R hat is not too good. Could run it a bit longer, but also not extremely bad. So we plot the results, and what I plotted now is that doesn't get bigger. The estimated abundance per kilometer square, and these values are certainly too high. The species is never that abundant. That means by just using the count data, we are probably not able to correctly estimate, to reasonably estimate abundance of that species. And so let's see whether we are able to do so if we add the detection on detection data. So here we run the second model, the combined one, and I just load the output now from a previous run. I did run it for the same number of iterations, and here already the R hat looks better. It's all below 1.1 for the covariate estimates, for example, and for the estimate of detection probability and the intercept of abundance. Then let's plot it. Yeah, and now you can see that the highest value are a bit higher than 2, or is more reasonable. In the data you have seen, we saw that in some sites the species was a bit more abundant, but still this is much more reasonable than what we had before. Yeah, and now to the second part. Yeah, we calculate some validation scores to be able to compare the two different model rounds, or the results of the two different analyses. Quickly run that because it takes some time, and then we can go through this function together. Yeah, and the figures that I used, they basically come from Houghton's paper, or Houghton and Hobbs paper. I have included that also. It's also in the Dropbox file. You can look it up there. Yeah, so the argument that enters is the outcome of the Jax model. Then here we extract the estimates for each iteration, of Jax. So not just the mean estimates or something, but really all the outcome. For lambda. Lambda is the estimated abundance. Then we just keep these lambda estimates for the sites where we have skipped the data, and now I'm lost. Sorry. Oh, and I think here it's about yeah, just I will execute it. It's finished soon.
So you can use this one, it's just from these 10 all our data points there, right?
Yeah.
Is that really that? I mean, I don't know, it's kind of very small form of data that you hold out.
Yes, if you really want to compare the models, you should use you should have higher numbers. That's for sure. I mean, here it's 10 sites, so yeah. Yeah, but we don't have data from all of these, our observation data from all of these, of course. So yeah, so these are the for each of the 300 iterations, we have 300 iterations that came back in the out object, and for each of these iterations and for each data point that we have skipped, we have then an estimate here of estimate for the count, considering latent abundance and estimated detection probability. And then here we calculate the first metric that is called log predictive density. So we go through all iterations, because in each iteration the latent abundance and also detection probability is estimated a bit differently, and therefore we go through all of these 300 iterations. And then we go over all left out data points, and then here on that line we estimate kind of how likely it is, given the estimated detection probability and the estimated latent abundance, that our model estimates really fit the true count. The true count that was, or the true number that was counted by the observer in the field. Yeah, so here we have these 300 lambda estimates, and we just take the one from that specific site and from that specific iteration, and fit the we use that as an input of a Poisson. Or so the result of that specific run would basically most likely be 0, but it could also be 1, 2, 3, and so on. And then yeah, with that we kind of check, yeah, how likely it is that we really estimate correctly. We calculate the mean of that. And yeah, we do that for all iterations, for all sites. And then that gives us, in the end, the log predictive density. And this log predictive density, this is this you can then compare between the two different models. And if it is higher, then the kind of predictive ability of that model is higher. So we can afterwards compare log predictive density between the integrated model and the binomial and mixture model. Then what we can also do is to calculate the root mean square predictive error between the predictions and the left out data. That's also something that we can compare between the two models, and here larger error is of course worse, so smaller would be better. And then in addition we can also compare the number of out of sample data that's correctly predicted, like for example the from the median estimate. And yeah, that information we can afterwards compare for the two different models. And yeah, if you you could run that by yourself, and then it really resulted that the predictive ability of the integrated model was much better than the one of the binomial and mixture model with the count data only. Yeah, but on the other hand, I have to say that yeah, as mentioned, the number of left out data is very was not much. So probably this is, in that case, it's not really honest to compare it, or it's not too informative to compare it. But if you do it with larger data sets, then that would be yeah, quite useful. Yeah, that's yeah, that's about it. Someone has something to add? Questions?
Yeah, I have a couple of questions, are more general, but so maybe you can all say whatever. But I was wondering, imagine that one of your data sets here is an already density, estimated density, like a monitoring program that was conducted independently, and they were obtaining like densities through other kind of sample, like distant sampling. So you have for some territories like the actual or the real, not real for sure, but with some uncertainty, you have already the data. And you don't want to model this abundance because you or density because you already know this density, but you want to include this in the model because you have later like more opportunistic data. You know what would be like the good like the best way to include this data in the model?
You kind of know the latent abundance already.
Say again?
You know the latent abundance already.
Yeah.
Like you perfectly detect the species.
Yeah.
No.
No.
You said when you have to take from a different estimation protocol.
Yeah.
You have like this, there. This is something or whatever.
Yeah.
For some of these sites.
Yeah, for another monitoring protocol.
Mm-hmm.
And you want to include just this data because you know that probably is okay. And you don't want to model actually this data. It's just to inform to the rest of the data set that you have that in this place is probably that the density is this exactly, or with some kind of percentage. You know?
Okay, and you do not want to make an integrated model, but just want to kind of make use of this data.
Yeah.
So then it would, or yeah, just an idea, you might fit the species distribution model using that separate data, and then use the outcome of the species distribution model as a covariate.
Those other, yeah, approaches that Marc was telling us, right? Yeah, the other ways to include data not by joint likelihood rather than including as a covariate.
Yeah.
Or as a predictor.
Yeah. Or what other options would there be?
I was thinking like for some sites, for example, just to put like okay, this site follows like a Poisson, but with lambda fixed, and the fixed lambda would be like the data that you have from the other monitoring program or something like this. I don't know if that would make sense.
What?
Yeah, you could do this. So you would have to separate probably the sites into those where you do have just the counts and those where you have these outcome from the first step of analysis. And then in a way, you then use the estimates, the point estimates. In a way, you would use the results of the previous analysis there as priors, as strongly informative priors, as informative priors in the new analysis. Yeah. So one way of looking at integrated models, some people, when Nicolas or others talk about integrated models, you put these different data sets together. Some people, we've heard some people say, oh, it's just informative priors, and that's not a way of looking at the integrated models. In a way, under certain conditions, you should, in a Bayesian framework, if you like, if you can analyze the data set separately, and then if you use the posterior distribution from one data, so the estimates from one data set as priors, informative priors into the next, and then into the next. In such a sequential analysis, you should, in theory, under some conditions, get exactly the same estimates as when you do all the analysis at once. And so with this idea in mind, yes, you have sometimes when you have some estimates, like you said, you put like input information from this previous analysis from the other data set in the form of data.
What also works is that you just input data about the latent occupancy state. That's the line here. A latent occupancy is basically conditional from latent abundance. So if abundance is higher than 0, then latent occupancy is 1. And you can actually enter data for that set. Yeah, and so also inform the model.
Okay. And the other question was like when you don't control really well the observation model, like for example, imagine that you have rather than counts, direct counts or detection non detection, you have like an abundance index because you were counting like signs or you were counting like drugs for animals. That would be the question. So you don't know how to actually transform those abundance indexes in actual abundance or density of animals. So I don't know if how those kind of data could be integrated in the model, like just allowing the model for a beta parameter.
Kind of a calibration parameter. Yeah, I think there are methods that use such calibration of one better data set and another less not that abundance explicit data set, but yeah.
Okay.
All right. So next break. When do you want to continue, Miguel?
As soon as possible. No. You're at 4 o'clock.
At 4. Okay, great. See you at 4.
Yeah, there is here the grade is typically don't find it more than one way. And of course, that you need longer estimation. This is yes. And the other aspect of experience is maybe they're not if that depends on there's some social component aggregation as this then I think this is I would not suggest more like that. Also, GLMs, I would say, yeah, because they are likely to or what would be a like a case well, I worked down. Yeah, I worked with some time ago. It's more of an aggregation, not necessarily a cloning. The non-random distribution. Yeah. What can we do? Two-dimensional spatial plans. That's also the one of the and with that you can of course account for spatial patterns and for okay. Yeah, so there's additional spatial well, an additional spatial pattern and population distributed. Okay. That picks it up very well. Okay. That makes the maps much better. Okay. Yeah. But is it adding a lot of experience? Costs a lot. Because it's really a lot of it costs a lot. Yeah, not much. And also, yeah, there is potential on the other hand, as it's going to start with analyze work analyze that. Of course, yeah, there is more. I think colors, it's really colors. Then offline some of these we could also after picking them whether in the slides no, we but it's one or road landscape or some area where you find so it's planting. Yeah, kind of. Yeah, there is also that I think is the way result doesn't that much, whether you use 5 points or not you use good slow down. Just quickly before we get going, if anyone's still got their name badge, there's a box on the table on the way out. And when we're finished,
Wahrscheinlich sind wir bei den Hühnern fertig. Jetzt müssen wir mal schauen, aber noch hier.
Das Problem, da können wir immer sagen.
Ja, Broken, ja, genau.
Okay, so now we have the last schedule. Yes, but let me see whether I managed to do that. Weißt du das mal? Der Dingskehr. Musst du auf die grüne? Okay.
Dass es vorher kommt und jetzt Screen und dann.
So. Okay, so. So that was the most difficult part. Oh. Going back. So now, well, we are in the last bit here of this workshop, and I want to show you like two case studies again with integrated models. The first one is we want to integrate recapture data with data recovery data. That also then helps us to show, or I can show there also how we can analyze these capture, recapture, and data recovery data to estimate survival. And then the second case study is then a true integrated population model. But let's start first with these capture, recapture, and data recovery data. So that are typical data sets, of course. You all know, of course, when we have marked individuals. So we have here marked bird, here a wax wing on the left-hand side. We can mark them and then we can recite them maybe next year. And then this produces these capture histories that we see here. So that's for each individual is a line, and each column may be a year, or it could be also another time step depending on how we have collected the data. 0 means the bird was not captured, the 1 means the bird was captured or seen. So the first bird here was first released or first marked in the second occasion, in the second year, was seen again in the third year, in the fourth year it was not seen, and in the fifth year it was seen again. Now we see from this capture history that the recapture probability has not been perfect, because this internal 0 here indicates that, well, in this year we have not captured the bird, although it was alive. Then there may be others like this one. These are often the most frequent capture histories in such a data set. Just mark them and never see them again. Right, so that's capture, recapture data set. Then we may also have data recovery data. So we can mark birds and they may die at some moment and may be found by the public, for example, and report the ring back. Then we get other capture histories. Just from looking at them, you cannot distinguish them from the capture recapture data set, but here we know, well, these are dead recoveries. So the first individual here was marked in the second year, and then in the fifth year it was found dead, and its ring is reported. And the second individual, this one, was marked in the first year and was never found dead. So we don't have any more information about this individual. Now, the key thing here is that both data sets, they contain information about survival. And if we have both data sets, we may want to combine them because this adds some more information. We may get some more precise estimates. And right, and that's what we want to do now. Right, so to do this, we will go step by step. So first we analyze the capture recapture data only, then we analyze the dead recovery data only, then we combine them with an integrated analysis, assuming that these data sets, they are completely or are independent. I just continue to say independent, although I know, well, this concept is a bit more difficult than we thought. And then finally, we will also analyze the data with another model, accounting for possible dependencies, meaning that the same individual could be captured and recaptured, but could also be found dead. So we will consider that also. And this this requests then another model. So we will fit 4 different models. So the first one is the capture-recapture model. And there are different ways how we can analyze capture-recapture data. The most efficient way is to use the multinomial likelihood. This may be not the most intuitive way to analyze this data, but it's the most efficient one. The most intuitive way may be to use a state-space model or a hidden Markov model, where we then model for each individual and each time step, the individual is like tossing a coin, and we estimate the probabilities of that coin producing a head or a tail. And this probability is the survival probability, and then there is another coin flip for the recapture probability. But if you use this model, then this requests that we have to loop over all the occasions and over all individuals. And if you have a lot of individuals, this is computationally quite demanding. And so therefore, we can use this multinomial likelihood, which where we first have to make a summary or another, like a summary of this data set, or to present the data set in a different way with the so-called M-array, which you see here. So what does that mean, an M-array? An M-array is usually, is a matrix. And in the first row here, we have the number, we have individuals that are released at in the first year or at the first capture occasion. And then we have here in the columns are the recapture occasions. So first column here is the first recapture occasion. So meaning that would be year 2. We have here 2. That means we have recaptured 2 individuals in the second year that were released in the first year. Then we have here 1. So this means we have 1 individual that was released in the first year and was recaptured in the third year for the first time. So this individual was not recaptured in the second year. And then the last column here tells us how many individuals were released in the first year, but were never recited, never seen. So these are 10 individuals. And then the second line would be all the individuals that are released at the second occasion. And so this one means we have 1 individual that was released at the second occasion and was first recaptured at the third occasion. So this could be also one of these individual here. So this individual, or these 2 individuals were recaptured at the second occasion and also released again. So this means they are released here at the second occasion, and they are emerged somewhere here in this line. And if you do that, then our data set here is just a matrix, and the dimension is just given by the number of occasions. The number of individuals that we have doesn't play a role anymore. So, and that's the big benefit. And now, how can we analyze this data? Well, we say now, like this M-array here, or the data, they are, we use the multinomial distribution, and with some probabilities, and these are the total number of individuals that have been released at each occasion. So, for example, here there would be 14 individuals here in the first occasion that have been released, because it's just the sum of all these individuals in this line. Now, the more complex part is perhaps these cell probabilities. So here we have again like this M-array, and we have here these different cell probabilities. So the probability to that an individual was released at the first occasion, is recaptured first at the second occasion. This is just given by product of the survival probability phi and the recapture probability p. Now, the probability that an individual that was released at the first occasion and was first recaptured at the third occasion is this expression here. So it has to survive the first year with probability phi. It was not recaptured then at the second occasion with probability 1 minus p. Then it survived again 1 year with probability phi and was then recaptured finally with probability p. Here we assume that all the parameters are constant over time, but you could also add here time indices. Well, and so on. And then we have also this part here. So that it is never, meaning that there are individuals that were released, that are probabilities that birds that are released at the first occasion were never recited or never seen. That's just 1 minus the sum of all the other probabilities here in this row. And yes, and then the multinomial likelihood here, not multinomial distribution, sorry, allows us to estimate these unknown parameters phi and p just from this data set. Now we want to go into the code and execute such a model. First, we load some packages. Here, the package JAX UI, which is used then to run JAX. And another one is the IPM book package. That's a package that we have created with our book, and it contains some functions and also some data sets that we use in our book. And this is also on CRAN, so you can download this if you need it. Right, and then what else? I work here with a simulated data set. We have here 10 years. Yeah, we simulate over 10 years. We assume that every year 50 individuals are newly released and marked. We have a survival probability of 0.6. Recapture probability of 0.5, and then also a dead recovery probability of 0.8. So you see, we simulate the one data set with which includes capture, recapture, and also dead recovery probabilities. And then we simulate data using that. These are mostly, I mean, the simulation here is not very difficult. They are just mostly coin flips. And so the individual that was released may survive with this probability, and then if it's still alive, it can be recaptured with this probability. If it's dead, then it can be sampled with this recovery probability. Note here also that's just I have given quite a very high value for the recovery probability, but this is just to, well, for demonstration to have some individuals that are recovered in the data set. In reality, this would be smaller usually. So now I want to run this. Okay, still okay. Create this data set. And then we look. We look at it. These are just the first 6 individuals. We see here the first individual was released at the first occasion, and then at the second occasion it has a 2. This means this individual has died and was found dead. This individual, the second one, was released at the first occasion, also was then not seen, and only on the 4th occasion it was recaptured again. That's indicated by a 1. Now, we only want to have the capture-recapture data, so we have to throw out all the 2s from the data set now, because our first model is just for capture-recapture, and that's what we do here. So data 1, we see we have in total, we have 450 individuals. So these are now the capture-recapture data of all these individuals. Next, we have to create the M-array. So that's a function now from the IPM book package. We do that. Then we see, well, we get this M-array here. So there are, well, in the first row here, we have 13 individuals that were released at the first occasion and then recited at the second occasion, and so on. So that's now the like the data set is much smaller, and which allows much more efficient computation. That's the JAX, the model written in JAX. The key part here is this multinomial likelihood. So the M-ray are our data. We loop over time, and then the parameters here are these pi. These are the cell probabilities of the M-array, and this rel here are the number of released individuals. This is also data. That's because we know how many individuals we have released. And then this bit here is just the calculation of these cell probabilities, which are functions of phi, the survival rate, and p, the recapture probability. And then here we also give priors. So initially these parameters here are written as time dependent. I make them constant here. I say, well, all of them all of these time dependent values are the same. And then we give priors uniform between 0 and 1 for these parameters. Right, and then we run the model. What happens here? Maybe I have not computed yet the number of released individuals. Perhaps that's the problem. Right. So we can look at the output. Here we get our estimate of survival, it's 0.622, and the recapture probability 0.46. These are these estimates. Now we go on. Next step is we want to use the dead recovery data to analyze, to estimate survival. Now the dead recovery data looks like that. We have already seen this. And again, for the dead recovery data set, we could use state space models, which again requires that we have to loop over all individuals over all time steps, which is computationally intensive. But we can also make an M-array for the dead recovery data, set. Yeah, and then it looks like that. So here the meaning is slightly different. These two means that they are individuals that are released at the first occasion, and at the second occasion they were found dead. And similar principle, we have the multinomial likelihood, we have the cell probabilities, and the cell probabilities are now differently structured, because here, so the probability that an individual that was released at the first occasion was found dead at the second occasion is 1 minus S. S is now the survival probability, so the bird has died, and then it was recovered dead. So R is this probability to find the dead bird. What about here? Well, this is the probability that an individual that was released at the first occasion was found dead at the third occasion. So this means this individual has to survive the first year with probability S. Then it died in the course of the second year with probability 1 minus S, and then it was recovered with probability R. Right, and the last thing here is again like the probability that individuals were never found dead. So now let's go to the JAX again and try to analyze this data set. Now we take again the same original data set, which contains the capture, recapture, and the dead recovery data. Now we take out all the recaptures and just keep the initial capture and the dead recovery. And that's what we do here. This is a little bit more complicated, but not very much. And then we use the, construct the M-array. Now the function here is slightly different to produce a dead recovery M-array, slightly different than capture recapture M-array, but there is also a function in the book package. And I have also looked at the M-array. Now that's the M-array for the dead recovery data. So if I would not tell you that this is an M-array for the dead recovery data, you would not be able to recognize the difference between that and the capture recapture M-array. Now let's look at the model. This is very similarly structured than the model that we have seen before. Key part here is again the multinomial likelihood, the M-array, P are the cell probabilities, number of released individuals, so that looks very much the same. Now the difference here is that the cell probabilities are different. Yeah, there's a different structure as we have seen in the slide before. We have S here, which and R, both of them are initially time dependent. Here I say they should all be the same, so constant over time, and then we give priors for them. And we can also run this model. And we have here an estimate of survival, again 0.62 about, and then our recovery probability, which is fairly high in this example. Let's go on now. Next step would be to combine the two. To make now or before we haven't made any integration. So now the integration starts. We jointly want to analyze the data set together. We have here the capture recapture data. We have the data recovery data. We have these MRAs. Now, what the key thing that we have to do is to give the same name to the parameter that is common, which is in our case would be survival. Initially, we had here written phi for survival probability. We replaced that by S because we use also S in the data recovery data. So that's the part that we change. And then let's look how the model. Let's look at the model in JAX. We have here these two MRAs. The one for the capture recapture data, and the other one MRA2 for data recovery data. So they are the same as we have seen before. Now, what about the model? Basically, now we have our two models that we have developed first. We put them all in the same JAX model. That's the first step to do that. And then we have to change some names, because initially we have named our data set for each data set just MRA, MAR, and now we have to differentiate that. We have to use different names. Otherwise, JAX will be confused. So I used always an index or a 1 here. I added a 1 here for the capture recapture data set. So that's the MRA, the capture recapture data set. The same also for the number of released individuals. And then also for the cell probabilities. So I renamed them as they are always P1. Right. But then the underlying parameters, they are the same as before. So we have phi and we have P. Now for the data recovery data set, we use the name MAR2, just to distinguish it from the capture recapture MRA. We have the number of released individuals 2 and then pi 2, so that they are different. Still have S, the survival probability, and R, the recovery probability. Now, what else you need to do? They are time dependent first. We want to make them constant. That's what we do here. And the key part is also where is it now? Is here, because here we still have the phi and the S, and we want to say at some point they should be the same. Yeah, because otherwise the analysis will be completely independent from each other. And here with this statement, we say the S equals phi. So that makes the integration between the two data sets. Otherwise, we give priors for all parameters, and then we can run the model. And now we again have estimate of survival probability. We have an estimate of the recapture probability, and we have an estimate of the recovery probability. So now we have made an integrated capture recapture and data recovery analysis. Now, but if you think about it, how have we done this? I mean, this is something that you would probably never do like that, because what we have created a data set, or we have sampled a data set from a population that produces capture-recapture data and data recovery data. And what we have done here now is to say, okay, we take all the individuals, all these 450 individuals, and then produce one data set from them where we only have the capture-recapture data set, the capture-recapture data, and then take the same individuals again, these 450 individuals, and just use the data recovery data. So we used, so we use the information that they provide about survival in some way twice. So we have made like, initially I would have said we have violated the independence assumptions. Now maybe I would perhaps better say, well, we make kind of a pseudo replication, because we use the same information twice. And now what we want to do is to account for that. So to make a better analysis that accounts for the fact that the same individual can be captured and can also be found dead. And to do that, we have to change the model. So now we have to use a multi-state model to do that. So these are our capture-recapture data set that I've shown at the beginning already. So one means that's a live capture and the two is a data recovery. And then we can use a multi-state model where, yeah, and we have here, or we need to have here like 3 states, which looks a little bit strange at first, because we have one state as alive, that's not strange. Then we have, but then we have 2 dead states, which if you see that for a first time, this looks a bit awkward. But still, I mean, we have one dead state. It's so-called recent dead state. That's a state where an individual, when it's dying, it's in this state. And then in the next year, it moves somehow to the final dead state. Yeah. And the reason why we do this is we have to make sure that individuals that are dead, that they can be sampled only once, and to because they can only be found one time dead and not multiple times, and to account for this, or no, to make sure that this doesn't happen, we have to include this additional dead state. So you can see here an individual may stay alive with probability S when it's still alive. It may become dead with probability 1 minus S, that's mortality probability. It cannot move directly to this long time dead state. But once it is recently dead, the individual, in the next time step, it falls into this long time dead state. And if they are dead, then they remain there. And then we have our observation matrix here. Individuals that are alive can be seen with probability P, or they may not be seen. And individuals that are recently dead, they can be recovered with R, but just this single year. Afterwards, they are not there anymore and cannot be seen. So, and dead individuals, long-time dead individuals, by definition, they cannot be seen. So again, the same principle, this multi-state model, multi-state data set, they can be analyzed with a state space formulation. Again, this is computationally not so efficient. Or we can use the multi-state M-array. And that's what we will do here. The principle is the same. It's a bit more complicated, because now, since we have 3 states, the first 3 lines refer to individuals that are in the first state, second state, and third state, and that are released in the first year. And then the next 3 lines are for individuals, again, in state 1, 2, 3, but they are released in the second year. So it's just like we have 1 dimension more in the M-array, that are the states. Yeah. So it becomes a bit more complex, but the principles are more or less the same. Then the probabilities of the M-array, again, also they look a little bit more complicated, but we can use matrix multiplication, and then we have like this structure here. So basically this thing here is that individuals that are released at the first occasion can be recaptured or can be re-encountered in the second occasion. Right, and this is expressed with the matrix multiplication of the state transition matrix psi here and the and the re-encounter matrix, which is this bit here. We also have here a matrix with non-encounters, so that's just 1 minus p or 1 minus r. We define this also, and then can use matrix multiplication to have this formulation here. Good. Now let's look into the code. First, we have to construct the M array from our original capture from our multi-state capture-recapture data set, which remember includes the 1s and the 2s. We also have to tell, since we have one unobservable state, the state 3, the long time dead state. This we will never, is not at the beginning in our data set, but we have to tell that there is an additional unobserved state. And so with the argument, with this argument here, we can tell the function here, the M array function, that it shall take one unobserved state. So we will do that. We can have a look at the M array. Now it looks quite a bit bigger. That's just because we have, if you want, each line and each row is multiplied by 3 because there are 3 states. Then the model is, well, there are different parts of the model, this multi-state model. The most important part is maybe this bit here. So this is definition of the state transition matrix. So we call this psi. So we have here a state transition from state 1 to state 1. That's the survival. Here is a transition from state 1 to state 2. That's mortality. And then transition from state 1 to state 3. That's 0. So basically, we just have to. Well, it's this matrix here, the state transition matrix that we define in JAX. And then we have here also the matrix with the re-encounter probabilities, P and R. And then this bit here is then, that's a multinomial likelihood. It looks similar as we have seen before. We also have here these cell probabilities. We have the number of released individuals. And this ugly looking thing here is just this matrix multiplication of the different matrices just to fill up these probabilities that we need to estimate survival and state transition. But that's written in a very general way. So whatever kind of multi-state model you want to fit, you don't need to touch this. So that's always the same. So the only thing you really, if you change the model, it's only really have to change these state transitions. All the rest is the same. Then what else? Again, initially these parameters, survival, recapture, and the recovery were time dependent. We make them constant and then give priors to them. Good, then we run this model also. Takes a little bit longer, not too much, I think. Well, it's Marc's computer, it's not the fastest, perhaps. So. Yeah. Okay, so that's the outcome now. We have survival, again, around 60%, and then recapture probabilities and recovery probabilities. We can have, let's look at the posterior distribution, perhaps, of the survival probability. You see here, that's a posterior distribution of the survival parameters that we have estimated on the different models. So the black line here is the capture-recapture model. Then we have from the dead recovery model is the blue line. And then we have from the integrated, where we assume that the data set are independent. So, or where we have made like the pseudo replication, as the red one here. And the green one is the taken into account the dependent, or taking into account that the individuals can be recaptured and recovered. Well, that's just a single realization of one data set. What I have done, and you have also the code then also, I have made a simulation. I repeated the whole thing 1,000 times and then looked at the outcome. And what we see here on the left-hand side is a box plot of the posterior means of these 1,000 simulations of survival under the 4 different models, and they look all unbiased. So that's good. Then what is interesting, if we look at the standard deviation, so at the precision of these survival estimates on the different models, you see here from the capture-recapture data set, it's, well, we have precision. Under the dead recovery data set, we have less precision. I mean, this is of course conditional on the specific values we have chosen. So the given recovery probability or recapture probability. So if you change that, then the ratio of the two here may differ, of course, also. Then when we have the integrated analysis, then now the precision that may be, it's interesting, of course, the precision is increased. So we get more precise results as you would expect it. And if you assume the independence, or if you make a pseudo replication, we get here more precise results than if you have really accounted for the fact that these are the same individuals that are recaptured and recovered. So that would be more correct one here. Yeah, this one is too precise. Good. Are there questions for this capture recapture? So I mean, I know it was very quick. Or yeah, Rahel. Yes, yeah, that's very true. I've forgotten to mention that. Usually, when you have to recapture individuals, we estimate apparent survival. So individuals that are moving outside and stay there, they are not accounted for. Yeah, and so typically, and you're right. I mean, the dead recoveries usually do not originate only from the study area, but from the whole world. So there is not this issue. And then usually, if you combine them, we can, this allows them to separate site fidelity and well, or to have an estimate of site fidelity and true survival. Yeah, but here, to make it simpler, I just assume that this is not an issue. Yeah. Then we go on for the second example, an integrated population model. So what we have here, we have collected demographic data, or from the individual level, from population, bird population, can you imagine? So we have capture-recapture data, and then we have productivity data. This means that perhaps we have visited nests and have counted the number of fledglings that each net has produced. And then we have also counts from the population, meaning that every year we have counted the number of breeding birds, or the population size. And we want to estimate, or we want to get insights into population dynamics. We want to estimate survival rate. We want to estimate productivity. We also want to estimate population growth rate. And we want to do this with an integrated population model. And the key idea really here is to use the count data. And we can think about the counts, because the change of the population size over time is a function of the demographic rates. So if you analyze counts, then this means that there is some information about all demographic processes in the population. And we want to make use of this additional of this information with our model. Now, how do we do this? Oh no, first comes a sketch here on an integrated population model. So an integrated population model, or how we see it, is always, there is a core part here, is the population model. Typically, this is an age-structured or stage-structured population model, which makes a link between population size and the demographic rates. And then we typically have some data from the population level, counts, time series of counts, and then we have data set from the individual level. Often capture, recapture data and productivity data, but there could be also other data sets. For example, radio tracking data can be also informative about survival. And right, and then we want to construct such a model. We assume here to have data on woodchuck shrikes. So some of you may have been lucky also to see it on the excursion on Wednesday. So this beautiful bird here. If you set up an integrated population model, I always think it is nice to think about 3 typical steps that we have to do. The first one is to define the population model, the stage or age structure population model. Then the next step is to write the likelihood for each data set that we have. And the last step is to make the joint likelihood. So to have the full integrated population model and analyze this likelihood then. So the first step is to build the population model. Now there are a lot of choices that we have to do here. And this depends, of course, on the knowledge of the species, depends on our question, and right, and may depend also on the data that we have. Here, the woodchuck shrike, it has a life cycle of a passerine, typical passerine birds species, so they don't have much age structure. So here we thought it's enough to distinguish just between 2 age classes. We have for the 1-year-old individuals, and we have what I call adult individuals, that are individuals that are more than at least 2 years old. Another choice that we have to make is when we look at the population, do we build a post-breeding or a pre-breeding model? Here we use a pre-breeding model, so this means that we look at the population before the reproduction starts. And so therefore, at this moment, so for the woodchuck shrike, this will be now, for example, the youngest individuals are really these ones. They are 1-year-olds. There are no younger individuals at this moment in the population. Right, another choice that we do is we make a female-based model. So we assume that the dynamics is just driven by the females. Right, and then we can write this, draw this life cycle graph. So an individual that is 1-year-old may survive with adult survival. It becomes an adult in the next year. Adults, they remain adults when they survive more years. And the blue lines here is the recruitment. So a 1-year-old individual can produce a 1-year-old individual in the next year. First, it has to reproduce. That's now, it's a little bit small. You know, it's if produce a number of offspring F1, yeah, because we assume here that productivity of the younger individuals is different than productivity of the older individuals. That's for F1. Because we just take the females, we divide by 2, and then these individuals, they have to survive with juvenile survival probability to become a 1-year-old individual in the next year. Adults, they can also contribute to recruitment, of course. They have another output. They have FA as their output divided by 2, and these young have to survive. And then we can write equations here for the number age-specific or stage-specific number or population sizes. So the 1-year-old individuals in year T plus 1 is a function of the individuals the year before times some demographic rates. So that's like a Leslie matrix model. If you want, that's deterministic here without demographic stochasticity. Often we want to include demographic stochasticity. This just means that we have to find some suitable distributions. For the recruitment process, we usually use a Poisson distribution, because Poisson distribution, of course, produces integers, and there is no upper bound. That's right. There's no upper bound, and the expected value is exactly that bit here, so corresponding to this here. Then for the survival or for the adults here, we have just a binomial, we use the binomial distribution. Again, this distribution produces integers, but it has an upper bound. That's the population size the year before, because there cannot be more adults than they were in the year before. And yeah, the expected value is the product of adult survival and this binomial total, which is this part here. Good. So we have now our population model, and you have seen, I mean, there are many choices and or assumptions or decisions that we have to make, but let's stick with this. Now the next step is to use to write the likelihood for each different data sets, and we start with the count data set. So we have the counts. Every year we counted the number of breeding birds, breeders, of breeding females, I must say, to be correct. And we will use a state space model for that. State space model are composed of a state process, which models the true dynamics of the population, and this is identical to our population model that we have just developed before. And then we have our observation. There's an observation equation which links our observation, our counts, which may have some errors, with the true population size. So for that, we use here the normal distribution. We can use other distribution. We can use Poisson, for example, or log normal, or yeah, there are some choices here. Here we use the normal distribution. We cannot distinguish the two the age classes when we count them. So we just know the total number of breeding females that were there. So it's a sum of 1-year-old and older individuals. And there is here some sigma parameter that's usually referred to as the observation error, but it's in fact it's more than that. It's a residual parameter. It also accounts for potential lack of fit of the model. Right, and the likelihood of the state space model is this. Well, I mean, just symbolically written. Then we have capture-recapture data set. We use the multinomial likelihood as we have seen before. So this M-array formulation. We may have this likelihood. I mean, here it's a bit more complicated than the model we have seen before, because we have an age structure here also. So we estimate juvenile and adult survival. And then we have the data on the reproductive output. For that, we can just use the master regression model. I mean, the data here are just the number of fledglings that have been produced by the by a mother, by a female, and we know the age of the females. So to be able to estimate the productivity for the 1-year-old individuals and for the adult or the older individuals. Right, and the next step, the last step, is to create a joint likelihood, which is assuming independence, which is the multiplication of these single data likelihoods, and then we can make this joint likelihood. We can use a frequentist approach, which to me at least, and also for you probably be more complicated. Bayesian approach is simple because this joint likelihood that we see here, we do not really have to write it explicitly. Good. Then let's look now to close this, and we use the other. You have this also, this other file here, integrated population model. Open this one. Again, there is this. Well, we have the libraries that we need to load, and there is a data set that is in the book package. This is a simulated data set. It's not the real data set that we will use. So it's the data set Woodchat 5, and need to load that, and then we can have a look at the data. Well, we have here capture history, the age or capture histories. These are 1,902 individuals over 20 years, so it's quite a fairly large data set. We have also the age of the individuals when they are captured, because this is needed to be able to estimate age-specific survival probabilities. Then we have the reproductive data or productivity data. So from 930 individuals, right? And then we have the counts every year. So in the first year, for example, it was 91 breeding pairs. In the next year, there were 119 breeding pairs. So this is quite a good data set, relatively long and large, relatively or reasonably large numbers. But as I said, it's a simulated data set. Good. What else? Then we need to create. We also want to make an MRA for the capture-recapture data set because this is more efficient for the analysis, as I mentioned before. Now we have to include age structure in the MRA, which is even more a little bit more complicated. And I won't go into detail for that. Just show again. I mean, there is a function also that can be used to create this age-dependent MRA. Maybe I just want to see here. I mean, here now, since we have two age classes, it produces two MRAs. One is for the individuals that are released as juveniles, and the other one is for individuals that are released as adults. What else do we need? I think that's. I think I don't. Yeah. Then we look at the model. Now the model for these integrated population models can easily become, the code can become quite long. That's a bit difficult part to keep the overview. But yeah, to keep the overview. In principle, what we do is if we would have written the single data likelihoods for each data set. We have already, for the capture-recapture data set, we have already had such a likelihood. In principle, we put all together and again give the same names to the common parameters. So that's again the principle that we have to do. But I would like to guide you a little bit through the code. We start with the state-based model. And the core part of the state-based model for the count data is our population model. So the process model of the state-based model is our population model. And basically we have these expressions here. So we say, well, N is our matrix for the population size. It has two age classes, so therefore 1 and 2, and it goes over time. So the 1-year-old or age class 1 in year t plus 1 is generated from Poisson distribution because we wanted to include demographic stochasticity. So that's why we have here this Poisson distribution. And then we have the expected value, or the expected value is just this expression that corresponds to our population model, which was that. Basically, that's this equation here that we write in. Right, and then for the second age class, we use the binomial distribution. We have here as the rate parameter is the adult survival, and as the total is the population size the year before. Then we have an observation model which links our counts. This is the capital C. These are the counts. We use a normal distribution. We the mean, the expected mean is the total population size. Now is these correspond to the sigma parameter. So that's the residual or the observation error or the residual variance. Now in JAX, this is a little bit strange. Somehow the normal distributions are parameterized with precision. So tau is in fact a precision and not a standard deviation or a variance. But yeah. But this just means then that we have, or we can work with the precision also and give a prior for the precision. But usually what we want to do is to give a prior for the sigma, for the standard deviation. That's what we do here, and then we we just calculate tau from sigma. Right, then we have here, this bit here, is the likelihood for the capture-recapture data sets, so our M-array, similar as we have seen before, more complicated because we have the age structure here, so we have 2 M-arrays for the juveniles and for the adults, but the same principle. And where is the, oh, I have to see also, here, I left this out. For the productivity data, that's maybe the most easiest part here. J are our the number of fledglings for each brood I, which is a function which is a draw from a Poisson distribution with F. That's productivity, and here the index is well, here it's the year. Sorry, I just see that this doesn't correspond directly to the slides that I've produced. Sorry for that, because on the slides you have like age-dependent productivity. Here I see it's just a single productivity measure, but it's year specific. Yeah. Right. So these are our let's say, well, these are the different signal data likelihoods. So for the population count data, for the productivity data, and for the capture-recapture data. And we see the integration works because we use the same parameters. So here we have F, the productivity, which appears in the likelihood of the productivity data, but appears also in the likelihood for the count data. Or here we have, for example, adult survival, which appears in the likelihood for the capture-recapture data, but appears also here in the likelihood for the count data. What else? We also give some priors. Well, first I make all the parameters constant, and then we give some priors here also that are assumed to be vague. Then we run the model. Again, performance test of Marc's computer. I will not run too long. Nope. Just want to see. Should have reduced maybe the number of no, here we go. So what we have here now as our result here are the estimated demographic rates, so mean juvenile survival, mean adult survival. P are the recapture probabilities, which are time dependent now in the model as I formulated. Then we have mean F, this is the productivity. And then we have here also the estimates of the population sizes. And we have the estimates of 1-year-old individuals and of adult individuals. That's sometimes nice to get insights into the age structure of the population. So because, as I said, when we count the individuals, we cannot distinguish the age class, but now we can get insights into the age structure. Of course, this is dependent on the way how we have defined our model. So if you would include more age structure in our population model, of course, then these values will differ. Right now, let's look at some graph here. What I show here as a graph, I mean, we of course, we can look also at posterior distribution of the demographic rates, but what I show here is just to the estimated population, total population size now, so the 1-year-old and the adults individuals summed. That's our estimate that we have here, mean with credible intervals, and the blue lines are the counts. Yeah. So just like looking at that, it's quite a good fit. And this is the state-space models or the integrated population models in general. They're very flexible. So usually you find something like that, so that the fit looks quite nice. If the fit looks not nice at all, you can be sure that something is wrong in the model, so that you have missed some part in the model, or yeah. But if you have like a nicer fit like that, it doesn't necessarily already mean that everything is good. I won't, yeah, just some warning also. But you see also that the population is fluctuating a little bit here, although the demographic rates have been constant over time. And this is just because we included we allowed for demographic stochasticity, the model. If we would have not done this, then we would have seen like a straight line, so straight increase of, I mean, an exponentially increasing population. Good. Now the next thing that here is also, that's what I mentioned before. Just look very briefly, because that's not so much interesting. Perhaps these are the posterior distributions of the demographic rates of juvenile survival, adult survival, productivity. Now, as a last exercise, now let's assume that we don't have productivity data. Let's assume we only have counts and recapture data, and we want to see whether we can estimate productivity from this data. So I load the data again without the productivity data now. Then our model, the only thing that I have to change is to take out the likelihood for the productivity data. So if I go back, recall here we had some statements here. So this bit here, this is the likelihood for the productivity data, and this we will remove from the model. We just delete it, and then we run the model again. Yeah. So the information about productivity now only originates from the count data. So I run this again. Again, a little bit waiting time, but again, not so much. Should be a little now, because there is one likelihood component less. Although I mean this bit is not is not a bit complicated one. Why? Well, our observation model is a normal distribution. So this means that we would assume that sometimes we count more than they are actually there. So it's not by normal distribution. So that's some assumption here. We think that on average the count, or by using the normal distribution, we assume that on average the counts are correct. So there is no shift, but we may double count some individuals in some years more, and in other years we may miss some individuals. So but this depends. The choice here depends really a bit on the sampling situation. But if you have just a single count of year, I mean, there is no way we cannot use binomial distribution, for example, because the detection probability would not be identifiable. Yeah. Yeah. Well, I think the normal distribution is, well, the nice thing here is that you have an additional parameter, the sigma, which takes up some lack of fit. And you can see if you observe this, if you change your model, and if this is dramatically changing, then you can more easily see lack of fit. I think. If you use the Poisson, for example, I mean, there is not this flexibility. Yeah, but yeah. But having said this, also, if the numbers or your counts is decently large, it's not very small, then usually when I often try out also taking one time the normal and one time the Poisson, usually there is hardly any difference at the end, so you cannot really see much a difference. So yeah, it's a bit difficult to give really let's say a final advice. Maybe the advice would be, well, try out different things and see whether things are very much different. And yeah, as I say, my experience is it doesn't matter so much in most cases. Good. Now we arrived here with the computation. We again have estimates here of the two survival rates. We have the estimate of productivity. Yeah, you see, although we don't have productivity data. And also we have estimates of the population size. So as before, but now let's produce a graph again, first for the population size, and then for the demographic rates. This looks pretty much the same here, so hardly any change as before. Now let's look at the posterior distribution of the demographic rates. And I think I took them or compared them from both models. Yeah. So IPM1 is the model with including the productivity data. IPM2 is that one without productivity data. If you look at productivity, then we clearly see, well, include data, then of course it's much more precise, of course, the estimate. And so we lose precision, but what is nice, I mean, we get the point estimate is unbiased. If all goes well, then we have here an unbiased estimate of productivity. Although we don't have productivity data. Yeah. So the information comes from the counts. The other parameters here look pretty much the same. Sometimes. Well, sometimes we lose also precision in some other parameters if we have data set less, but more, yeah. So we see, I would say, or claim, well, like we have like two, I think I have this on the slide also. We have two key benefits of the integrated population models. One is the precision of the parameter estimates is usually improved because we don't have only information from the individual level data set, but we also have information from the count data. But often also this is, having said this is also often relatively tiny because the information in the count is usually not so strong about the demographic parameters, and it's difficult to fiddle this out. And so often the gain in precision is often not so strong. Yeah, but I mean conceptually there is an improvement there. Then the other thing is that we can estimate so-called hidden parameters for which we don't have explicitly collected data. So as we have seen for the productivity or for immigration, as we have discussed in the course of this conference. Of course, with these hidden parameters, we have to be very careful because they are latent parameters, and they easily suck up lack of fit in other parts of the model. So we have to make sure really that the other things work well, and yeah, otherwise they may be biased there. What else? So the model that I've showed you, I mean, we can make it more complex. For example, we can include temporal variation in demographic rates. So include environmental stochasticity. We can model also environmental covariates, of course. We could include that in the model. We may also include density dependence. So this we have also seen during the conference. so that the demographic rate is a function of the population, of the estimated population size. So that's also possible. What can be done also is we can make predictions into the future. So usually population, or in the past, let's say, population variability analysis have been done like first we estimate demographic parameters, we take them with the uncertainty and we write another model and make a population variability analysis. Here with the integrated population models, we can do all at once. So the model that we have written now, we simply have to extend some loops in our population model. And then like this, we can make predictions into the future and we account for the uncertainty that we have in our parameter estimates. So that's quite a handy thing. So we don't, yeah, we can do all at once. What can be done is also retrospective population analysis. So life table response experiments. This was also mentioned a couple of times here in the conference. That's something that it will not do inside the integrated population model. So you will take the estimates from the integrated population models and then do this life table response experiment afterwards. So, I mean, of course, I have to say this, I like integrated population models. They are very powerful, they make a lot of sense, but also we have to be careful, of course, when we use them. We should assess the fit of the model. Unfortunately, there is not so much development for assessing the fit of integrated population models. There are some ideas around. Usually what we recommend is to look at the fit of each single data set because they are well developed goodness of fit tests, for example, for the capture recapture data set. Yeah, and for the productivity data where we have used Poisson regression models, we can use goodness of fit tests for Poisson regression models, for example. Right. So for this should be done, or we always recommend that this should be done. That what is also quite useful is that you analyze also the single data separately. So if you do not write at once an integrated population model, start with the capture recapture data, then analyze productivity data, and only then put them together, because this helps for the model development. This is easier like that. And on the other side is also, you can compare then the survival estimates, for example, that you get from the capture recapture data set alone with those that you obtain from the integrated population model. If they are drastically different, then I would be a bit suspicious. Alarm bells maybe should call, and you should be, yeah, you have to check then again what's happening. Probably then some assumptions are violated. Right, and the interpretation of population size can also be tricky. We have discussed this already a little bit. So because usually when we have a single count, we cannot really estimate detection probability. We just can make some smoothing with using normal distribution or Poisson distribution, but we cannot make this shift. If we systematically miss individuals, we cannot make this shift. And so therefore, population size that we estimate here may be true population size if we have a very intense count, but in most cases it will be the relative population size. So yeah, the population size multiplied by the detection probability. Right. Yes, I would. Huh? To simulate data, no, it's well, this is doable. I would say it's not so complicated, but it may be if you have a very complicated model with a lot of data, then they tend to run for a long time. So it can happen that it takes some hours and or days even. Huh? And if you then want to simulate data and repeatedly analyze it, this could be a really big challenge, just from the time point of view. But of course, yeah, data simulation on the Euring model would be helpful to find some yeah, some problems. Yeah. Right, I think that's about what I wanted to say about integrated. Here is some advertisement also. Marc and I will give a workshop on integrated population models, a weekly workshop in Missoula in the USA next or this summer. So if you are interested, there are still some places. And then we also have a postdoc position at the Vogelwarte, which will analyze or really use integrated population models to analyze some data set on alpine swift and pied flycatchers. And there is, the application deadline is relatively soon, but it's still possible to apply. And I think in the slides that you have got, you can see the links, or you can use the links if you are interested.